All right, yeah, so this is a comparison of Jupiter and Saturn. Notice they're not that different in size, and they have the same exact interiors. It's just the scale of the interiors is different, meaning the rocky core in here is significantly bigger on Saturn, but the liquid metallic hydrogen is smaller and the molecular is bigger. So it's just the proportion of each of them has changed. Okay? All right. And Saturn also has many, many moons. We're not going to talk about this now. In fact, what we're going to do is I'm going to get through all the planets, and then we're going to come back and talk about some of the most interesting moons in the solar system. We're going to talk about a couple of them for Saturn. We're going to talk about Titan, and we're going to talk about Enceladus, both as being very interesting ones. But I don't expect you to know the moons of Saturn. But we will talk about the rings and the rings in more detail. In fact, we're going to talk about them right now. Because that's what makes Saturn cool. And Saturn in a telescope is one of the funnest things to ever look at. Back when I built my own telescope when I was 14 years old. I had a grandfather that was into amateur astronomy, and he got me all excited. He lived in North Dakota. I grew up in Montana. We would go visit him about once a summer. And then we'd go out at night and look through his telescope. He built his own telescope, and that was the coolest thing ever. So when I was 14, I built my own telescope with help from my dad. And I actually built a little observatory on the roof of our garage. I built stairs. You came up through a hatch into it. It was great. And yeah, it was kind of funny because then I went to college, but I never intended to be an astronomer, but it just kind of happened. I actually went and taught high school for a year and teaching physics, and then I realized I was getting paid nothing for teaching high school, and the only way to make money as a high school teacher is usually to get an advanced degree like a master's degree or higher, because then you get paid higher. So I went back to get my master's degree. Well, I could be in anything, and I went back into astronomy. I loved it so much, I kept going and got my PhD in astronomy, and then I became a professor in astronomy. So, funny how things happen. But here I am talking about Saturn. What do we know about the rings? Well, the rings are composed of chunks of ice. And this is just plain old water ice. I mean, there's different types of ice. There's carbon dioxide ice or dry ice and other ice in the universe. But this is water ice. Water, remember, water is a very common molecule in the universe. Okay? It's a very stable molecule, and it's a very common molecule. We find it everywhere. And so this is just ice chunks. And each one of these rings is not solid at all. It's just composed of millions of these little chunks of ice. And every one of those little chunks is orbiting Saturn in its own orbit. So, I mean, if you really wanted to be picky, you could say that Saturn has hundreds of thousands to millions of moons, because every one of those particles is actually orbiting Saturn out in space. Most of us don't say that. In fact, we're not really sure. There's not a designated, oh, you have to be this big to be a moon. But they don't consider the ring particles as moons, even though that's really what they are. And so there's these chunks of water ice. Well, the good thing about ice, as you know, is it's highly reflective. And that's why we see these rings so well, is because the sunlight reflects off them very easily. Ice is a very reflective molecule. Notice there's gaps in the rings. There's different reasons for different gaps. The bigger gaps I will talk about because they're caused by a very special thing. Most of the smaller gaps are caused when you have a bigger chunk coming through. So most of the particles are very small, from like marble size, sand grain size, up to chunks of rock, but occasionally there's like house-sized rocks, chunks of ice going around, all right, bigger chunks of rock. Well, when they do, they kind of, as they orbit, they kind of clear a hole behind them, and then the material slowly flows in behind it. We know that the ice ring particles seem to slowly be migrating towards Saturn. So over time, they run into the atmosphere and get burned up in the atmosphere of Saturn, and we know that they're a transient event. They're not a permanent thing. Meaning they're going to be there for a long time, millions of years, but eventually the rings will go away, or they'll get down to a very thin, narrow rings, which is what we see around like Uranus and Neptune. Meaning that the rings were just much older around Uranus and Neptune. These nice broad rings here that we see means this is a fairly new development. And this can happen around all planets. We see it around the Jovian planets, but there's no reason why a terrestrial planet can't have rings as well. Okay? Now they just won't last for a long time. So where did these chunks of ice come from? Well, the speculation, we don't know for sure, but the speculation is something called the Roche limit. Yeah. What they found was, here's the planet, here's Saturn, that if there's anything inside 2.5 times the diameter of the planet, if there's a moon that's inside here, too close to the planet, then that moon feels massive tidal forces as different parts of the moon get pulled on differently. And over time, that's going to rip the moon apart. And so if there was a moon that was inside this distance, it eventually would get ripped into tiny pieces. And if it was a moon that was mostly made of ice, all those pieces of ice would still be orbiting, but they would get ripped into all these tiny pieces and they would make a ring. So our current idea is that one of Saturn's moons, one of its icy moons, most of its moons are very icy out there, okay? There's some that are different, but lots of them are just chunks of ice. Got close enough to Saturn, got within this magic Roche limit, this 2.5 times the diameter of a planet. That's called the Roche limit. That's the limit to how close you can be to a planet without the tidal forces ripping it apart, especially for a large planet. A large planet like Saturn, a lot of gravity there. Yeah? So, we don't find moons inside there. The moons could go in there temporarily, but they couldn't last. They can't stay in orbit in there for a long period of time, so they'll get ripped apart. So a moon could go through there and not get ripped apart, but if it stays there for a long time, the tidal forces will rip that moon apart. That's called the Roche limit. All right, so let's look at the rings. So here we are. I'm going to try to draw the ring system. So here's Saturn. And the main ring system, so here's the rings. Okay, there's a gap in the rings right here. Let's do one that's not so close up here. This is a perfect example here. All right, you see this gap right here? That's this gap right here I'm drawing. There's an actual gap. It's not just dark material. It's an actual gap. You can see through it. You can see Saturn through it on the other side. All right? That's called Cassini's division. Named after Cassini, who was a French astronomer. Was he French or Italian? He was one of those, astronomer. That was the first one to see it. And then they named the mission after him, the mission that they sent to Saturn to study, the Cassini mission after him. So, from the Earth, what you can see is really these 3 rings here. And this outer ring, remember we're not very creative, is called the A ring. This is called the B ring. And then inside is the C ring, right here. And the C ring is more right here. Okay? The B ring is the brightest ring. You can see it's significantly brighter. So this is the A ring, Cassini's division. B ring, this is the C ring right here. Okay? This is another division right here. This is called Encke's division, but we won't worry about it. Let's talk about Cassini's division. Well, what causes Cassini's division is there's a moon out here called Mimas, or Mimas. And it has what we call gravitational resonance. With any particle at the distance of Cassini's division, which means Mimas goes around Saturn, but it goes around exactly twice for if there was a particle in Cassini's division, it would go around once. So they were exactly synchronized. By the time it went around twice, it went around once, this one went around twice. I did that backwards, sorry. By the time Mimas went around once, a particle in the ring would go around twice. We call this a 2-to-1 resonance. And you're like, what does that have to do with anything? Well, what that means is, Mimas, this moon here, M-I-M-A-S, is going to pull on a particle in the ring every time time at the exact same spot. So if there's a particle in that ring, it feels a little tug there every time it goes around, and it does it at the exact same point in its orbit. Because of that, essentially it clears it out, it moves it out, it moves it a little further out, and then it becomes part of the outer ring. So any particles that are in here, over time, Mimas is going to move them out. They're either going to go in or out so that they're not in resonance anymore. I like to think of resonance as pushing a kid on a swing. If you push a kid on a swing, you always push them at the same part in their swinging. So they swing out, they come back, and then as they're going forward, you push them. And so every time you just add a little bit more, and they get higher, and they get higher, and they get higher. Okay? But if you were randomly pushing, like you push it once here, and then you push it once when you're up here or somewhere over there, it wouldn't go anywhere. You would make them actually stop because you're pushing them all at random times that's not in synchronous. But if you push them always at the same point in their periodic behavior, you're going to change their orbit. And that's called gravitational resonance. So it's gravitational resonance that creates Cassini's division. It also creates Encke's division. It's just a different moon. All right. Back to the rings. When the Voyager, actually Pioneer went there first. Pioneer's 10 or 11. Went to Saturn. So I'm back to my ring picture. They found there were a lot more rings than these 3 rings. There were a bunch of rings you could see that were not visible from Earth. But before I get to that, I want to show you this picture. This is different sides of the planet. So one side of the planet and the other side don't match, which shows the rings are not actually circular, they're elliptical. Which makes sense because remember, Kepler said all things orbit on elliptical orbits. So one side looks